An important part of being a mechanical engineer is understanding how to transform rotating power into electric power. And now for many, many years, well over 100 years, I'm thinking now about 150 years, the steam power plant process has been a tried and true way to convert rotating power into electric power, which is used worldwide, of course. And also, if you're thinking about, well, I don't want to go work for a power company, I fully understand, but do recognize that the production of electric power goes way beyond simply working for a power company. In industry and throughout the world, there are employers and organizations that produce their own electric power, many times independent of a power company. So chapter 8 is called Vapor Power Systems, and what I call it is basically steam power plants. And so in this module, I'd like to help you get started with into chapter 8 by recapping what you already knew. Let's go ahead and do a quick recap of things you already know, things you've already mastered in this class. So, what's the objective of a power plant, and what kind of expenses would you expect to have? You've seen this slide before. Your main objective, if you're responsible for working at or managing any type of power plant, is to produce electric power for consumers or your internal customers. That's the energy sought. That's what you're seeking to do. Now, what's your main expense for running a power plant? Other than salaries, perhaps the cost of fuel or source energy. That's what really is going to be one of the major budget items of running a powerhouse or a power plant. And that would be considered the energy that costs, wouldn't it? Energy sought and energy that costs. If you watch my videos, you know what's coming. Well, if you know the energy sought and you know the energy that costs, you've defined the thermal efficiency. And so let's review what you already know about a system operating in a cycle. Let me move my picture here. I think that'll fit pretty good. Remember that schematic. You've got Q dot H. That's going to be the energy sought. It's coming into some black box, some system operating in a cycle at a steady rate. You're making some measure of net output power, W dot, but because by the second law, you can't convert all of that heat energy into power. You must reject some of it. And so that completes the schematic. So you remember, well, what was the best possible? What's the best possible thermal efficiency I could get in the real world? Well, the best possible thermal efficiency is described by your high temperature heat source, TH, and also where you're rejecting the heat to, your low temperature heat reservoir, TL. And so the maximum possible thermal efficiency is described by TH minus TL over TH. And that would be if somewhere you could purchase a Carnot cycle. Of course, you can't do that, but if you could purchase a Carnot cycle, you'd be in the money and you'd be operating at maximum thermal efficiency. And so if we go to the left of the slide here, you say, well, for a realistic power plant, the thermal efficiency is the energy sought, W dot net, the output power divided by the heat added. And by the first law, the numerator becomes Q dot H minus Q dot L. That's a statement of the first law of thermodynamics. Another little recap, and just remind yourself, how would you take a set of open systems, steady state, steady flow, and how would you put them together to build a system operating in a cycle? And so here's how you do it. You'd buy yourself a boiler, a device that operates at high pressure that takes in heat energy, Q dot H, and it transforms boiler feed water, compressed liquid, into superheated vapor, high pressure superheated vapor. Well, that superheated vapor then is going to be piped to a steam turbine. and that steam turbine is going to drop the pressure. It's an expansion process. We're dropping the pressure and extracting energy in terms of enthalpy from the steam, going to a much lower pressure, and we're causing a shaft to turn at a high speed, and that shaft will run a generator, and you make all kind of electric power. Well, you say, well, that's not the end of it, because we can't just spew all this low pressure steam into the atmosphere. We have to condense it so we can get back into the boiler. Thus, underneath the steam turbine, you're going to find a condenser where we're rejecting heat from the low pressure steam, and that low pressure steam is condensed. And at least on this picture, you see, well, it's by gravity, it falls out of the bottom of the vessel as saturated liquid, and it's going to flow into this boiler feed water pump. And so here's a picture, boiler feed water pump. It pumps that liquid back up to high pressure, compressed liquid, and there you are back to your boiler. So those four pieces of equipment is what's going to enable you to create and run a power plant. Just kind of a recap. Makes sense? Let's see, what do those four things have in common? Those four pieces of equipment, they're all running at steady state. They're all open systems, steady state. And let's see, they're all one inlet and one outlet. So you can be pretty masterful at analyzing each of these and putting it all together. Let's see how to put it all together. So let's start with a sketch, and let's start with our turbine. And so what I'm going to do is work you through what we call the Rankine cycle, the basic cycle for a steam power plant. All right, so here's a sketch of our turbine. It's like see, the pressure is decreasing from 1 to 2. That's why I'm showing it's an expansion process. See, W dot of the turbine. So you might say, well, where's your Q dot? Where's your Q dot in 1 to 2? I haven't shown anything, have I? That's because this turbine is going to be modeled as fully insulated. Okay, so there's our turbine process. In at 1, out at 2. Next step, let's add a condenser. So we're going to go from 2 to 3. This condenser is just a large cylindrical vessel. That's all it is, large cylindrical vessel where we are rejecting heat from the low pressure steam, and as it condenses, it becomes saturated liquid. So gravity, the condensed steam falls to the bottom of the vessel because of gravity, and that's where we go to state 3 as saturated liquid. And here I have depicted Q dot, haven't I? Q dot is going to the low temperature reservoir. In the condenser, I don't see any W dot. That makes sense. The condenser is not lifting a weight. There's no shaft coming out of the condenser. We go into the feed water pump, and you see that I've depicted it as a centrifugal pump. You can go back and maybe look at some of my previous videos. I am showing W dot of the pump is less than 0, even though I'm showing my W dot arrow going out. At least I'm saying W dot is less than 0, going out to state 4. Okay, let's see. All we got to do is finish it up with the boiler. And so we're going to pump our feed water up to the boiler, inlet, compressed liquid to the boiler. We're going to add heat, Q dot H, from our high temperature reservoir TH, and then off we go back to state 1 as superheated vapor. And let's see and W dot net. How am I going to calculate W dot net to get my thermal efficiency? I'm simply going to add these two W dots together, recognizing that this one's a big positive number and this one is going to be a small negative number. That's where we get our net power from. Another thing, this is a little bit of a review, but recognize that what we've created is a closed system operating at a steady rate. That's kind of an important thing to recognize. I've drawn my control surface around all my pieces of equipment. So you see, let's see, what have I got passing through the control surface? I've got Q dot H coming in. I've got Q dot L leaving. And on my sketch, I probably should have pulled that dashed line a little bit more to the left. And I've got, I've got W dot net penetrating the control surface. Maybe I did do a good job of this. W dot turbine plus W dot pump is going to be W dot net. Okay, so do recognize we've got, by taking those four pieces of equipment, open systems, putting them all together, we've created a closed system operating at a steady rate. Hope that helps you get ready to go into Chapter 8. Okay. First law, as a reminder, here's our schematic, and we've already talked about this as our recap. Q dot H minus Q dot L is W dot net. You can figure that out. It's not exactly a formula, it's a fundamental. You can figure it out by looking at your schematic. And then for those of you who are graduate school bound, the cyclic integral of heat in equals the cyclic integral of work out. Okay, that's the Rankine cycle. Now let's draw the ideal Rankine cycle on the TS diagram, because you're going to be doing this over and over and over again in Chapter 8. For the ideal Rankine cycle, let's start with the turbine. Here's a vertical line, 1 to 2. That says we've got a constant entropy turbine. Turbine is reversible and adiabatic. Okay. 2 to 3, that's the condensation process in the condenser. Recognize here at state 3, we're at saturated liquid. So we're talking about the ideal Rankine cycle here. 3 to 4, we've got a reversible adiabatic pump. Adiabatic and reversible. Notice here, just by observation, the Rankine cycle, state 4, is going to be a compressed liquid. There's no getting around this. It's compressed liquid coming in at state 4, coming into the boiler, the steam generator, constant pressure process, 4 to 1. Steam generator, you can think of it as a big vessel with lots of tubes inside it, adding heat into those tubes where we're generating superheated vapor from a compressed liquid. Okay, process 4 to 1, constant pressure. Process 2 to 3, that's the condenser process, constant pressure. That's the ideal Rankine cycle. Now, let's kind of join the real world a little bit. Now, ideal cycle analysis, very important and powerful. We're going to add a little sophistication to this. We're going to say our turbine is no longer reversible and adiabatic. We're going to say it is adiabatic, but irreversible. So that's how come we have this dashed line, 1 to 2 actual. And in my world, I call this 2I, 2 isentropic. The textbook calls this 2S, and the textbook calls this state 2. In my world, I have to keep myself straight by having 2A for 2 actual and 2I for 2 isentropic. Same condensation process to saturated liquid, pump, also adiabatic, but irreversible. So do you see that state 4 is going to go a little bit to the right of 4I because there's something irreversible going on in the pump. Okay, and so 4A will be the inlet state to our steam generator, and then we've completed the cycle again. And so this can have some power for you to get into your mind. What does a realistic Rankine cycle look like? And I've tried to show what the little pictures of the equipment look like as well to help you get this into your mind. So who was Rankine in the first place? Who was this? We call it the Rankine cycle. Why is it called the Rankine cycle? Well, it's called the Rankine cycle in honor of the man who came up with this proposal. His name was William Rankine, and this is a bust of Rankine shown in Randolph Hall. And so I've shown the Rankine's bust over top of the traditional Rankine cycle with reheat at the turbine, with superheated vapor at the turbine inlet. Okay, Rankine cycle. I hope that you have some interest in learning a little bit more about who was William Rankine in the first place. I took this photograph back in Randolph Hall, where there was still a Randolph Hall. Extraordinarily interesting. And so as I was an undergraduate, this became part of our daily life, is walking past Rankine's bust. This particular bust was created and dedicated by the class of 1902. Imagine that. Class of 1902 put this into motion to have Rankine's bust created and dedicated here. And now Rankine's bust, along with this dedication plaque, is on the 4th floor of Goodwin Hall, right outside the Mechanical Engineering Department office. Please go have a look, read the plaque, and if you're interested, go to Wikipedia and read up a little bit about who was William Rankine. Just a recommendation, if you find history of engineering interesting, you'll find his story interesting, I hope. And so now it's time for a little bit of a roadmap of what's coming up on Chapter 8. We're going to start out with the most basic Rankine cycle has saturated vapor at the turbine inlet. When I'm teaching the class, I don't spend much time on this very basic ideal cycle because it's unusual in the real world to go into a turbine with saturated vapor. Very unusual. So in my class, I skip very quickly to the ideal Rankine cycle with superheated vapor going into the turbine. Next step is to add a little real world to that, have the Rankine cycle with an irreversible turbine and feed water pump, just like I showed on that second TS diagram. Now, you're going to get good at that. About halfway or 60% through the chapter, we introduce what's called regeneration, or in other words, heating of the feed water by taking some steam from the turbine. Instead of going all the way through the turbine, we take some steam and we use that steam to preheat the feed water before going to the boiler. That is commonly practiced in most power plants. And then finally, a last topic is reheating the steam. Once you go into the turbine and you get some power out of the steam, you take that stream and you go back to the boiler and reheat the steam and then go back to the turbine. That can be a little complex, but you're going to have homework problems probably with all of these examples of regeneration and reheat. If you're eager to say, I'm ready to get going with the computations, I have worked out, now I see it's 51 minutes, a 51-minute video to get through one worked out homework problem, problem 816 in your textbook. So if you're eager to see, I'm interested in seeing how all the numbers shake out, you can go to, let's see, homework solutions playlist, problem 816 will get you a demonstration of how do you work out all the numbers, all the details, all the first law, second law analysis, continuity equation for a very traditional Rankine cycle with superheated vapor and adiabatic but irreversible pump and turbine. So that's your overview of recapping what you already know, overview of what's coming up in Chapter 8, extraordinarily powerful concepts that you're going to learn about and practice in your homework problems. Allow plenty of time to do your homework problems for this chapter because the computations are tedious, lots of property lookups, and so I have to be unapologetic saying that that's the way it goes when you are working in the production of power using steam as the working fluid. So I hope that helps you get started. I hope you get some level of enjoyment out of Chapter 8 and perhaps be thinking about, might I be interested enough to work in this type of area as a job?